Hello, my name is Dr. Richard Head, and I'm going to talk to you today about how we measure time of day. If someone were to ask you, what is the time? You would likely look at the corner of your computer screen, a clock on the wall, your wristwatch, or maybe your mobile phone to see what the time is. If we assume the time is 0900 hours, you might reply, it's 9 o'clock. This reply is perfectly good enough in most circumstances. The person you are talking to will know it is the morning, and hence it can't be 9 p.m. They will thank you and be on their way. But what if you are talking on the phone to someone in another country? Let's say you are in the UK and they are in France. French time is 1 hour ahead of UK time, so you might say it's 9 a.m. UK time, or it's 10 a.m. French time. Things would get more complicated if you were talking to someone in India. In the UK and France, the clocks are moved forward 1 hour at the end of March, and back again at the end of October, whereas no such change is applied in India. So the difference between UK and India clocks changes depending on the date. What I am talking about are time zones. A time zone defines local time for a certain geographical area, typically aligned with state or country borders. Time zone definitions are thus political definitions, although they will also take account of longitude, so that noon local time is not too far from when the sun is at its highest point in the sky. Time zones are defined in terms of offset from UTC. That's Coordinated Universal Time, plus, for those time zones which use it, when and by how much clocks are advanced and retarded to implement daylight saving or summer time. Now, those of you bothering to pay attention will be wondering why Coordinated Universal Time is not abbreviated to CUT. The reason for this is that in French it is called Temps Universel Coordonné, which would abbreviate to TUC. So, UTC is a compromise which manages to offend the British and French equally. So, what exactly is UTC? Well, apart from being the timescale upon which time zones are defined, it is also approximately solar time at 0 degrees longitude. In other words, it is directly related to the rotation of the Earth, and that creates its own problems, because the Earth's rotation is not constant. But I'm getting ahead of myself. Why are there 24 hours in a day? Well, it appears the Egyptians divided day and night each into 12 parts, although these changed in length with the seasons. The Greek astronomer Hipparchus is credited with suggesting fixed-length hours, pretty much as we use today, around 140 BC, although lay people continued to use seasonally varying hours. It wasn't until mechanical clocks started to appear in the 14th century that fixed-length hours fell into common use. The division of hours into 60 minutes and minutes into 60 seconds derives from the Babylonians, who seemed to have a thing for the number 60. Perhaps because it is exactly divisible by 1, 2, 3, 4, 5, 6, 10, 12, 15, 20, and 30. Once again, it was mechanical clocks which brought this into common use. Now, I'm sure it will come as no great surprise that the early mechanical clocks were not particularly accurate. The idea of measuring the length of one solar day to the nearest millisecond was simply not practical. So clocks would be corrected against the sun. Now, if you were to find yourself suddenly transported back to the early 1800s, whilst having a modern, accurate digital watch in your pocket, you would find as you wandered from town to town that clocks were not synchronized with each other. The idea of a national standard for time was first applied by the Great Western Railway in England in November 1840. This was aligned with time at Greenwich, that is, Greenwich Mean Time. Other nations with significant developing railway infrastructures, such as India and the US, adopted a similar approach, with national time standards based on an offset from GMT. The basis of our current system was in place, and all this trundled along fairly well until the introduction of practical atomic clocks in the 1950s. This allowed accurate measurement of the actual length of a day, and the approximate rate at which the length of the day was changing. A new atomic timescale was adopted in July 1955, although it was not until the 1970s that its current name, Temps Atomique International, TAI, was adopted. Unlike the naming of UTC, it was decided to offend the British and not the French. In 1968, the definition of a second was changed from a fraction of the length of the year 1900 to a count of vibrations of the cesium-133 atom. Now, it turns out the current definition of the second, and hence minute, hour and day, approximately matches the Earth's rotation in about 1850. Until recently, a solar day was roughly 2 milliseconds longer than 24 hours. In the 1960s, leaps of 50, 100 or 200 milliseconds were applied to keep civil time in step with solar time. The name UTC was adopted in 1967. This system of corrections to UTC of fractions of a second was a bit of a pain in the butt. So in 1972, the system was simplified. Adjustments would be via whole seconds. This is the system we still have in place today, which uses the following timescales. UT1. This is basically solar time, determined by astronomical observation of distant quasars. Quasars are chosen because they are both bright, and hence relatively easy to observe, and very distant, and hence, for all practical purposes, remain in a fixed position. This set of fixed reference points is known as the International Celestial Reference Frame, or ICRF. And by observing the ICRF, it is possible to determine the Earth rotation angle, or ERA. Now, the duration of a single rotation of the Earth varies throughout the year, mainly due to the Earth's elliptical orbit. Near the March and September equinoxes, a solar day is roughly 20 seconds shorter than 24 hours, whereas near the June solstice, it is about 12 seconds longer than 24 hours. And near the December solstice, it is nearly 30 seconds longer than 24 hours. Obviously, it would be damned inconvenient to have different lengths for every day of the year, so these are averaged out over the year to determine mean solar time. TAI, atomic time, nowadays measured by a collection of atomic clocks, corrected for the gravitational time dilation effects to mean sea level. If you want to know more about gravitational time dilation, see my previous HED talk, number 1, the universe. UTC, a whole number of seconds offset from TAI. That offset being adjusted as necessary so that UTC is within 0.9 seconds of UT1. Such adjustments to this offset are known as leap seconds. And to complete the picture, there is the GPS timescale, as used by the Satellite Global Positioning System. That's the system that makes your sat-nav possible. This was introduced in 1980 and was aligned with UTC at that time. At that time, the offset between UTC and TAI was 19 seconds. Since then, the UTC-TAI offset has grown as more leap seconds have occurred, but the GPS-TAI offset remains, and will forever remain, at 19 seconds. And here is one of the things which makes me really angry. Doommongers saying that leap seconds cause problems for the GPS system they don't. Such claims are a load of tosh, because the GPS system uses GPS time, which does not have leap seconds. And whilst we're on the subject of things which make me angry, no, computers do not have a problem handling leap seconds. It is the humans who are too idle to properly program them that have the problem. It's actually relatively simple to program in leap second support. I've done it myself. Even Microsoft Windows has handled leap seconds since 2018. There haven't actually been any leap seconds since they added support, and there may not be for quite some while, because, it turns out, the Earth's rotation has recently sped up. So much so, there may eventually be the need for negative leap seconds. OK, up till now, I've just referred to leap seconds. Suddenly, I've introduced the concept of negative leap seconds. So perhaps it is time to more accurately define what a leap second is. I have previously mentioned that there is an offset between TAI and UTC, and when this offset changes by 1 second, this is a leap second. When the system was introduced in 1972, UTC was defined as offset 10 seconds behind TAI. Since then, there have been a further 27 leap seconds, each of them increasing the offset, resulting in a current offset of 37 seconds. Increasing the offset requires adding a second to the end of the day, on the last day of either June or December. This is a positive leap second. When a positive leap second occurs, 23:59:59 UTC is not followed by 0:00 UTC the following day. Instead, an extra second, 23:59:60, is inserted. Now, note the leap second is applied to UTC. So when a leap second occurs at the end of June, 23:59:60 UTC is 0:59:60 BST in the UK or 5:29:60 IST in India. But what if the TAI UTC offset needs to be reduced? That is, a negative leap second occurs. Although so far this has never been required, the system allows for it by simply omitting the 23:59:59 second. In other words, 23:59:58 would be followed by 0:00. It's all very well saying leap seconds are used to keep UTC within 0.9 seconds of UT1, but who makes that decision? It is the International Earth Rotation and Reference System Service who, twice a year, January and July, check the relationship of UTC and UT1 to determine if a leap second will be required at the end of the next June or December, and publish the conclusion in their Bulletin C. As of the start of August 2022, the difference between UTC and UT1 is 37 milliseconds and falling, so no leap seconds are likely to be required in the near future. And so there you have it. UT1 is derived by looking at the sky. UTC is an offset from TAI, which is derived from atomic clocks. And when the two drift too far apart, the International Earth Rotation and Reference System Service tell us to insert, or possibly remove, a leap second next June or December. And local time around the world is a simple offset from UTC, and in some territories this offset changes during the summer months. Thank you for listening, and have a good time.